I'm Henry, this is Jonathan,
Hey guys.
and we're doing an ops perspective into our journey with Elasticsearch and indexing 200 million daily records and how it went. So let's get started.
So Elasticsearch at eXelate, a little bit of background about our journey and what we had to deal with it. We started with Elasticsearch way back when with version, I believe, is 0.9b. It's been a lot of fun growing with the product and a little challenging as well. So we started out with basically just a requirement for our product. We had to find a database that could sort of house all of our data, allow people to do filtering, queries on it by whatever way they wanted. Also needed to be a highly scalable database. We needed to load to it aggressively, query it with low latency, and have it be highly reliable because, well, we in the infrastructure team don't like anything ever going down. So, sorry, I forgot to mention why we needed this. This was to be the brains behind our DMP.
Yeah, so this is, you can pretend that this is a mock-up because this is one of the early pages that we put together in the DMP. So what you can see right here is we're filtering on a certain tag set of tablet users. You can see that in the top left there. We're seeing about 3.3 million users, the majority of which are male and female between the ages of 25 and 34. So this is the kind of data that we want to be able to display through our DMP, and we needed a database that was able to back this. So how did we go about picking Elasticsearch? That's a great question. And it's really funny, just talking to people out front before this started, they were asking, why didn't you try this and this? And that is exactly what we did do. We tried a whole bunch of different solutions, and they all had trade-offs between performance and query latency, scalability, reliability, and so forth. So we settled with Elasticsearch back, as Jonathan said, version 0.9b, which has come a long way from there. So what exactly is Elasticsearch? Elasticsearch, you may know from your own products, it's a search engine. And it allows you to have real-time data analytics and real-time data streaming out of it, document-oriented storage, an inverted index search and full-text search, distributed storage and computation, and is also highly available. So right here is a diagram of our production cluster, and I'll kind of work you through it a little bit. Down in the bottom left there, you have our DMP API nodes. So these are the nodes that actually do all of, they allow the users to query Elasticsearch in a certain way. They provide the interface. What they do is they talk to an Elasticsearch reporter node. So the 4 nodes across the bottom here are non-data nodes. They do not house any data that is stored in our Elasticsearch cluster. So the reporter is actually the interface between our HTTP API and Elasticsearch. In the middle there, you've got 2 master nodes. So they govern the cluster so that they make sure everyone knows who's in charge of everything. Down at the bottom right there, you've got the data pipeline. That is how we actually get data into the cluster, which we'll talk about momentarily. In the middle here, all these other nodes, those are our data storage nodes. So we have 32 cores per node, 60 gigs of RAM each, and 1 terabyte of storage per node. This is all in Amazon Web Services, so we can scale this up and down as needed. With the combined 20 nodes, we have 640 compute cores, 600 gigs of allocatable heap, and about 20 terabytes of storage. That's 100,000 IOPS of compute power.
So back to what was our need before. So we were told to find a database that basically be able to query every which way, slice the data however you like it. So we could filter by various tags. It's plain search engine. We could do that. That's not a problem. We could filter by date ranges. We could do our aggregate queries. We've built our infrastructure in Amazon, so we've already got high scalability out of the box. And not to mention Elasticsearch itself is incredibly flexible. But that brings us to the next requirement of being able to do actual counts on our users. So to do counts on all of our data, that meant that we had to get all of our data into the database, which for those of you who know the industry and big data is always the biggest problem. So we figured, okay, so how do we get through this challenge, really, the indexing challenge?
So I'll give you a background, a little bit of how the loading process works. So it's a 5-step process. We start out by fetching all the user events from the previous day, and we launch the needed instances in Amazon Web Services. We then, all of our data is user event driven. And so we'll see any given user multiple times over the course of a day. So the best thing to do is reduce that all down into one user object with multiple events attached to it. So we run that through an EMR elastic MapReduce process to optimize that. The next thing we do is actually do the loading itself. So we have a custom Java process that's written, and it does all of the movement into the cluster. After the loading's completed, we'll do an optimize on the cluster using built-in Elasticsearch resources. And then finally, we'll do a backup process where we take a snapshot and push that to Amazon S3.
So this brings us to the indexing challenge. How do we manage to balance our ability to index data into the cluster, its indexing performance, with query latency? So initially, we decided to try and go for streaming the data. We wanted real-time analytics, we wanted real-time data. Let's load it into the cluster all day long. The problem was, no matter how big we built the cluster, we couldn't quite optimize it to handle the inbound data volume and also respond to queries in a reasonable time. So if we get all the data in, but you can't query it quickly, it kind of defeats the purpose. So how did we get through this challenge, sort of the balancing of indexing performance versus query latency? We thought about it long and hard, and we decided that we just don't. We didn't do it. We're not going to try and balance them. We're not going to try and make them run at the same time. So we decided to try and schedule them. I mean, the end goal was a platform that is a DMP, and our clients are only awake at certain hours of the day, not counting our API clients. So this gave us a work window. If we could squeeze all of our indexing down into just a few off hours at night, we're going to be good here. We could actually optimize our cluster into two opposite extremes. So what we started from was, all right, how about we start from just optimizing the cluster purely from an indexing perspective. See if we could index a full 24-hour data set into our database in 3 to 4 hours. So first thing we did was start tinkering around inside Elasticsearch. So we disable what's called the refresh interval in Elasticsearch. So what the refresh interval does is it's basically a mechanism in Elasticsearch that once you index a new record, it makes it available for searching. Now, since we're doing an aggressive batch load of data, we don't want that happening. It's expensive, it takes resources, so we say, you know what, Elasticsearch, don't make the data available at all. We're just going to index right now. So we turned that off, and immediately we saw our indexing rate went up. Great, but we're still sitting at about 15 hours to load a days of data here, so it's not good enough. So basically, we started peeling through bottlenecks in the system. So the next thing we found was that Elasticsearch itself was actually throttling us. There's a setting called store-level throttling. Now, before I could explain what that does, let me go a little bit back into sort of Elasticsearch. So we've got Elasticsearch, and it's got all this data, which is managed underneath by Apache Lucene. So in there, you've got all of your segments. You have your data organized every which way. There's a setting in Elasticsearch called the merge factor, which basically decides how much cruft can I have in any segment before I have to optimize it? How many deleted documents can I leave on disk before I say, all right, it's time to clean up? How many records that aren't, just well organized can I leave before we decide, hey, let's optimize. Let's do, I guess, the equivalent of a defrag on the cluster. Now, this is something that happens in the background in Elasticsearch all day long, and usually is pretty good to keep up. But what we found was we were actually indexing much faster than this process could run. So Elasticsearch started to employ its own defense mechanism and say, okay, you're going too fast. It would throttle us down. So we said, okay, stop. We disabled that completely, taking a huge trade-off on subsequent query performance by saying, don't organize the data neatly. Just get it in. Just get it all on disk. And boom, suddenly we're indexing even faster. And this is where we started hitting our next bottleneck, and this is one of the easiest bottlenecks to hit, which was IOPS. We literally redlined all of our volumes, and they weren't able to get any more transactions done. Now, when you're built on Amazon, that's really nice and easy, because you say, give me more IOPS. So we cranked it up. I think we started from 3,000 IOPS and then 4,000 IOPS, and right now we're sitting at about 100,000 IOPS total across the cluster, which is good enough for now. But we might need more. We're very excited that they're now offering up to 20,000 IOPS on their volumes. So we take care of that, and then suddenly we hit another bottleneck. We're loading even faster. At this point, we're well within our 4-hour window. Everything's great, but we could still do more. But the next problem we encountered was heap space. We were actually exhausting the entire system's heap, trying to index so aggressively, and well, let's just say that was a fun one that we're still struggling our way through. Well, let's go to the next slide where we encounter why that was a problem. So we've disabled earlier all of the settings in Elasticsearch that make it optimal for search, so that we could index as fast as possible. But now it's the start of day, and we want to optimize everything back towards query performance. So the first thing we do is we re-enable the refresh interval. We say, okay, make the data available for queries, right? Because we need to be able to see it. Great. Now, I mentioned earlier that we've disabled all of the things that prevented us from putting data into the system so fast that it's a mess. Well, we've made a mess of things now. Now, we have two options. We could just re-enable the background process, let Elasticsearch do its housekeeping, right? Clean up. We found that that took about 23 hours, which is not very useful if you're loading data every 24 hours. So that wasn't good enough for us. So we said, okay, fine, let's go a different approach. We called the Elasticsearch API. We said, go ahead and do a full optimize. Now, if you take one look at the Elasticsearch documentation, you'll see a big red banner over that that says, do not run this. Be warned. If you run this operation, this will use up as much resources as possible. It's essentially an unthrottled operation. It says, just go nuts, clean everything up. You can use all of your I/O, you can use all of your CPU, all of your heap for this one operation. Now, this means that query performance takes an absolute tank while you're running this. It'll time out on you. But it takes about 30 to 40 minutes, and boom, once we're done, our cluster is fully optimized, all of our data is neatly packaged, and we're now in optimal query performance land. The last bullet point over here is a fun one and brings me back to my point earlier about us running out of heap space. So we discovered a very interesting thing. If you are to index to Elasticsearch in a very particular way, where instead of updating documents, say you got a new record on an existing user, and you're not going to update it, you're just going to delete that user and add a new record with all of the data in it. That's sort of absurd, if you will. The background process that handles all the mergers I mentioned earlier, and also the one that gets rid of deleted documents, doesn't. This is a bug. It's a known bug identified in Elasticsearch and Lucene that they have solved in version 2.0, but not in any of the prior versions. And since 2.0 was only released 3 days ago, we haven't had a chance to install it. So what does this mean? Why does this even have any impact on our system? This brings us to sort of what Elasticsearch does with the deleted document. So when I delete a document out of Elasticsearch, it doesn't go anywhere. It stays right there on disk. It gets flagged as deleted, and it gets picked up by a background process later. In the sense that doing the delete right now isn't necessary, it's costly, so let's not. So Elasticsearch deprioritizes that and lets the background process handle it. But when you load in this particular fashion, that background process simply skips it. So suddenly, we started to have an increasingly larger and larger amount of deleted documents sitting on our database, using up disk space. But they did more than just use up disk space, because every time we fired a query into the cluster, say, hey, how many of these users do you have? It would go in and it would open up all the deleted documents as well, and then see they're deleted and not respond with that for the query. But it had to do all of this extra work. And this extra work started to steadily put a greater and greater strain on our cluster. Suddenly, we found that we couldn't even index as fast anymore, because we were running out of heap space. And why are we running out of heap space? Why are we using so much heap? Well, it turns out that we were spending more time opening up and ignoring deleted documents than we were opening up relevant documents. We were actually at about 50% of all of the documents on our database having been deleted already and simply stuck on disk. So, oopsie. We went ahead and dug into the documentation, and we found that apparently if you explicitly call the background process and ask it to expunge deletes, it will. But that's the only time it'll do it. So we started running that every day. And this removed our final bottleneck. Now we're not running out of heap space, we're not running out of everything, and we can go ahead and index and query away. So we're all set to go. We've met our goal so far. So we got filtering done, we got all of our functionality done, we've got low query latency established. Great. But now on to the next challenge.
Reliability and disaster recovery. So everyone has a hosting provider, whether it's in-house or, let's say, Amazon Web Services, that goes down every once in a while. You might remember Amazon's DynamoDB incident from about 2 weeks ago, which kind of wreaked havoc on them. Maybe you do, maybe you don't. But it's always good practice to have an alternative. So we built out a secondary failover cluster in an alternate provider's data center. So our internap data center is in Secaucus, New Jersey. It's bare metal cloud, so a little bit different than VMs scaling up, scaling down. We physically have the servers. They were spec'd out as close as possible to the AWS nodes. So we have the same master nodes reporters, the same APIs, and the only difference with the actual data nodes is we have about 2x the on-disk storage capacity, which we'll get into in a little bit. So here's the question. We've got this cluster, it's built, that's great. How do we get data into it? There isn't just a press the button and it happens kind of thing in Elasticsearch. So there are a couple options. Option A is to index to both clusters. So you can run the same pipeline against the secondary cluster, and you'll end up with all your data existing in both, and there'll be zero downtime, which is really what you want out of a failover cluster, zero downtime. But there are a couple downsides. Unfortunately, this requires, as I said, 2 indexing pipelines, which can be kind of costly and, from a compute perspective, expensive. The other thing is that your data might actually fall out of sync. If one of those pipelines has errors in some way or another, you'll end up with differing data. And what we really want to do is provide the most accurate data to our clients. Lastly, and this is a big one, is network latency. If we ran an Amazon data pipeline against a cluster that does not exist in Amazon land, that's over the public internet. So you might be using a VPN tunnel or a direct connect, but either way, you're still going to have some sort of latency. And that can actually really affect your indexing performance. So as we said before, we want to get this all done in off hours as quickly as possible. So that might be one of the bottlenecks that we don't want to introduce into the failover cluster. Let's go on to option B. So snapshot and restore. This is Elasticsearch's built-in backup mechanism. So you're able to target a local file system, a Amazon S3 bucket, a Microsoft Azure data store, et cetera, et cetera. This does a 100% binary backup of your data, your cluster, up to that day, and it's incremental. And you're able to do an incremental restore back onto the target cluster. That sounds great. That's exactly what we want, except for one thing. The indices in the failover cluster must be closed when you actually perform the restore. A closed indice cannot be queried. Therefore, your failover cluster now has 1 to 5 hours, depending on how long your restore operation takes, of downtime every day. So we just defeated the purpose of a failover cluster. So let's move on to option C.
Option C, the unholy marriage of two. So we couldn't run two pipelines. We didn't want to run two pipelines, but we couldn't quite do snapshot restore either. Anything that involved closing the indices and not having the database went right out the window. So we did something that's a little bit of both. So in our, say in our production cluster right now, we have one index, let's call it tags. It has tag data. When our API queries it, it goes, hey, give me whatever you have from tags and column this, and et cetera. So we went to our failover cluster and we leveraged a neat little feature in Elasticsearch called aliases, where you can simply create an alias and point to a different index behind it. So we downloaded a full snapshot from, say, October 30th onto the cluster, and we tagged it as tags. So now I have October 30th data on my cluster, it's tags. Now it's October 31st. I've just finished loading everything into my production cluster. I took my snapshot to S3. I've optimized the data. Remember, we mentioned earlier that we spend a lot of time optimizing the data to make sure it's all neatly compact. But this is before we took that backup to S3. So the backup to S3 is just a picture of the cluster with all of the data already neatly packed and organized. So this is great. Now we can restore all of this to our failover cluster quickly. So what we've done is we've restored it, but we renamed it as we restored it. The data is from the 31st, so we name it October 31st. It's great. It's easy. We can download the whole new data set while still serving the old data set to the APIs throughout. And then when we're done, once everything's been restored, we simply rename the indexes. Now, the index rename operation itself in Elasticsearch is atomic. So just like that. And now we've moved on from yesterday to today. 0 downtime. Problem solved. Hooray. Your sysadmins get to sleep at night. So just to recap, the needs were to have a flexible database that allowed you to filter by, and we've really slimmed it down here. There's a lot more filtering options than those three. We've got a scalable database. We could scale horizontally. We could scale vertically. We could do it in Amazon. We could do it elsewhere. We're able to index all of our data well within our allowed window. And just to point to that, as we scale the cluster horizontally, our indexing capacity goes through the roof. So that's all open-ended there. We've got low query latency by introducing all the optimizations, and we have reliability, both from Elasticsearch's built-in reliability of having replicas of all the shards and very high fault tolerance, and also having 2 physical clusters in different geographic regions. So should somebody make a mistake with the backend databases on Amazon again and take down EC2, or should somebody accidentally cut a fiber line in the middle of New Jersey, we'll still be up and running. Any questions? Anyone? Oh, we went too far.
We're putting you in the dark. There we go. Yeah, if anybody has questions, just raise your hand, and we've got microphone runners on both sides. Carl Bunch? Really?
All right. What were the documents? Is it a user profile and all of the segments and all the information you have on a user? You could maybe just a little explain.
Essentially, think of it as just a unique user and then comment the limited values.
Okay, and then you're just basically indexing all the values inside of it and then allow people to query all the things. They get the whole user back from the query.
They could get the whole user back, or if they want to do aggregate level counts, they could do that as well.
Cool. And you're deduping user IDs.
Ideally.
Can you just talk a little bit about how cost impacted your choices, like very early on, and like what data systems you would use and your overall architecture?
Well, cost was actually a lesser factor for us in the initial decision, as was flexibility and scalability. For example, say we could get an Atiza, but it takes 6 months to deliver them and things like that. We needed a platform that was agile, mostly because when we were first handed down this assignment, we had no idea how much data we would end up putting in it. I mean, I said we started on Elasticsearch 0.9, but I didn't mention we started on a 4-node cluster with only 8 cores a pop. And it worked for that limited use case, but we scaled up dramatically from there, and we're probably going to keep scaling too. So it was really looking for the most flexible system that we could find.
Yeah, especially in Amazon, you're going to spend a little bit more for that capability to expand versus a bare metal cloud provider where you're going to, you pay what you get, right? It takes a little while to expand out, though.
We do have actual runners with little carts plugging servers in over there, but it's still not as fast as EC2.
Hi. Can you talk a bit about the queries, like what applications they came from, parallelism of the queries, performance of them?
So all of the queries are being run by our own API, which is pretty handy because both the data structure of the indices and what we're going to query out was designed by the same R&D teams. So they kind of married the two together. I can't go into great detail into what exactly they're querying because that's just not my field of expertise. I do know that what the equivalent of a single query to the API translates into about 250,000 requests to the Elasticsearch cluster, which then come back and then get all merged together and presented on a pretty little page like the one you saw earlier.
Hi. So I was wondering, you said you have different optimizations for the settings for indexing versus querying. Do you guys do like a restart on the node to change those settings, or is it a hot swap?
No, all of these settings are dynamic. You can set them through the API in runtime. There's no need to restart any of the nodes because they're not persistent. Well, you could make them persistent, but you shouldn't.
One more over here.
Have you noticed a change in query performance as you've scaled out horizontally or as you've gone into bigger servers?
We did. And this mostly seems to tie with our actual heap allocations. As we continued to scale both horizontally and vertically, the cluster itself had more heap space to work with. Now, this was only an issue with our heaviest queries that would tend to exhaust that and it would sort of do this juggling routine, trying to get all the data out. Once we scaled to a point where we had sort of more enough heap to spare, we stopped seeing that kind of issue and we just saw excellent query performance. Or at least we saw the query performance correlate directly to how well we've organized the data on disk versus how expensive the query was computationally.
You've been using Elasticsearch for a long time now. Have you come to any limitation, and have you maybe considered moving to another technology since?
I mean, I'm always open to moving to new technologies. I'm happy with Elasticsearch, but we've also had our growth pains. I am looking forward to trying out their new 2.0 version that not only solves a lot of bugs, but I really enjoy the fact they have built-in Slack notifications, so I can shut down my many monitors.